Hello, I'm Seema and welcome to part 19 of the chapter The Solid State. In the previous video, I started discussing the electrical properties of solids and I told you that there are three kinds of solids, that is, conductors, insulators and semiconductors. I explained conductors, how metals conduct electricity to you, where I told you that there is a valence band, the different atomic orbitals of metals, they kind of superimpose on each other and form molecular orbitals. They are not true molecular orbitals but kind of molecular orbitals, and these molecular orbitals, since the number of metal atoms is huge, is really large, they do not appear to form proper molecular orbitals, but it appears to form a band of energy. So that band, which consists of valence electrons, is known as the valence band, and the next higher energy level, that is the molecular orbital or the band that is empty, is known as the conduction band. In the case of metals, that is conductors, the valence band and the conduction band are very, very close to each other. At some places it even superimposes, they kind of superimpose on each other, they kind of mingle, they have an overlap, area of overlap. So the electrons, the partially filled, in the case of metals, the outermost shell, that is the valence shell, is not completely filled. Therefore, it appears, this valence shell appears to, since it is incomplete, it has vacant places where electrons can move. Therefore, conduction of electricity is as it is possible, because electric current or conductivity is nothing but moving charges. But due to the close conduction band, the electrons move from the valence band to the conduction band very easily. They can easily slip into it, and therefore metals are good conductors of electricity. In the case of insulators, I explained that the distance between the conduction band and the valence band is huge, and the electrons cannot jump up to the conduction band, and the valence band is complete, kind of complete. Therefore, there is no chance of the electrons to move around freely. If electrons cannot move around freely, if charges cannot move around freely, electrical conductance is not possible. Therefore, such substances are insulators. So in this video, we are going to talk of the third category, that is conduction of electricity in semiconductors, or semiconductors as they are pronounced. In the case of semiconductors, the distance between the conduction band and the valence band is less. They are not merging, they are not overlapping, but they are not so distant as in the case of insulators, but it's kind of moderate. So on giving a little energy or on passing a little electric current, the electrons from the valence band can jump up to the conduction band, and this can result in somewhat conduction of electricity. It's not a proper conduction of electricity, that is why we do not call them conductors. We say they are semiconductors. They are conducting somewhat. Right? Now, the problem is that semiconductors can conduct electricity. It is like, imagine that there is a student who wants to be a doctor, and he's not that brilliant topper of the class who could just be a doctor. He is kind of moderate, but his desire to be a doctor is very strong. So if he gets the right kind of guidance, and if he works a little harder, if he gets the right kind of push, a little electric current that's giving the push, the moderate student can come up to that level where he can enter a medical college. It is somewhat like that. The electrons that are present in the valence band, on passing electric current, some of the electrons can jump up to the conduction band and result in the conduction of electricity. But this is still not enough, still not useful enough. So it is as if the student who is trying to go into a medical college can be slightly better, but he can still not enter the medical college. He needs another push. So what do? We bring in a teacher. You bring in me. So I start teaching that child, and when I come, I was not there between the book and the student. I came in as an impurity. So this impurity, or call it a catalyst, in other chemical reactions I prefer to call myself a catalyst, but not in this case. So this impurity that comes in helps that more electrons to go into the conduction band, and or makes the mobility of electrons easier. And that is why the semiconductor, from being very low in conductivity, its conductivity improves and it can be practically used. In its natural form, semiconductors are not used much. They are not of much use. Examples of semiconductors are elements of the 14th group, that is silicon and germanium. They are known to show semiconductivity. So let me just read this part. The gap is so small between the valence band and the conduction band, so some electrons jump to the conduction band and show some conductivity. It's very little. But conductivity, what would happen to conductivity if you increased the temperature? If you increase the temperature, the energy of the electrons will increase. If the energy of electrons will increase, more electrons can enter the conduction band. Therefore, conductivity of a semiconductor can be increased by increasing the temperature. So if you increase temperature, the conductivity can increase, but still, semiconductors are not good enough conductors to be of any practical use. Therefore, some impurity is added. So silicon and germanium, now these are semiconductors naturally. So we call them intrinsic semiconductors. You remember when I talked of intrinsic, the word intrinsic, I told you that when there is no, whatever the defect is, when we were talking of defects, line defects and crystal defects, I told you that an intrinsic defect is when nothing external is the cause of the defect. The defect is due to the substance itself. So intrinsic semiconductor would be pure silicon or germanium. The pure elements, they are semiconductors, and they are semiconductors because they naturally do not have a tendency to be very good conductors. And only few electrons can jump up to the conduction band to conduct electricity. So when you have intrinsic semiconductors, they are not very useful. So what do? You improve the conductivity of intrinsic semiconductors. And how do you improve it? By adding an impurity. That added impurity is, this process of adding impurities to semiconductors to improve their conductivity is called doping. The term that is used is doping. So conductivity of intrinsic semiconductor is increased by adding an appropriate amount of a suitable impurity. You can't just throw anything into the mix. Okay, this is silicon, this is germanium, so I want to improve their conductivity, let me throw the pen into it. That's not how it works. So you have to choose the impurity. What are you doping it with? The substance has to be chosen, and the amount. That is, it has to be appropriate, and it should be in the suitable, it should be a suitable impurity, and it should be an appropriate amount. This process is called doping. Now, impurity can be of two types. A semiconductor, you can improve the conductivity of a semiconductor by introducing more electrons into the mix, into the element. Or you can also increase the conductivity by adding an impurity which has lesser number of electrons. Okay, so we say impurity, if it has more electrons than silicon or germanium, it is called an electron-rich impurity. And if the impurity that is added has less electrons in the valence shell than silicon and germanium, then it is called an electron-deficient impurity. Both kinds of impurities will help silicon or germanium, that is the semiconductors, to improve their conductivity. So let us understand these one by one. Let's finish the sentence first. Impurity, the doping is nothing but adding an impurity which is electron rich or it is electron deficient, and introduce electronic defects in semiconductors. These impurities, whatever impurity you are adding, whether it is electron rich or it is electron deficient, it causes electronic defects. The number of electrons in the crystal changes. So it is not a stoichiometric, like in the case of defects, we talked of stoichiometry, stoichiometric defects, non-stoichiometric defects, where the stoichiometry that of the elements present in the crystal is affected. In this case, the composition kind of remains, the impurity, of course, it is an impurity defect, but the number of electrons, the ideal number of electrons, the defect will either increase the electrons or it will decrease the electrons. depending on whether the impurity is electron rich or is it electron deficient. So we come to the first kind of doping, which is called electron rich doping with electron rich impurities. Now we know the 14th group elements like carbon, silicon, germanium, they have 4 electrons in their outermost shell, that is, they have 4 valence electrons. So whenever a substance has 4 valence electrons, it can form 4 bonds. We know carbon is tetravalent and it forms 4 bonds. Every carbon atom forms 4 covalent bonds. The same happens with silicon and germanium also. They should form, ideally, they should form 4 bonds because they have 4 electrons in the outermost shell. So if you imagine this to be silicon crystal, it's not silicon atom, it should be a silicon crystal. So silicon crystal should have, every silicon, if you look at this, it should have 4 electrons in the outermost shell, and it forms 4 covalent bonds with the 4 neighboring atoms. This should be extended further. If you look at this central atom, it has 4 electrons on 4 sides, and 1 electron is from this atom, 1 from this atom, 1 from this atom, and 1 should be from the atom beneath it. So every silicon atom will form 4 covalent bonds, just like carbon. Carbon is tetravalent. The same situation happens with silicon too. So ideally, silicon or germanium should be forming 4 bonds. So silicon and germanium are group 14 elements. If in their crystals, each atom forms 4 covalent bonds with its neighbors. We know they are tetravalent, therefore they form 4 covalent bonds with their neighbors. When you doping is adding an impurity. Instead of silicon atom at places, you are adding an electron rich impurity. Elements of the 15th group have 5 electrons, 5 valence electrons. 14th group has 4 valence electrons. 15th group elements have 5 valence electrons. So if you add an impurity like phosphorus or arsenic, which have 5 electrons in their outermost shell, if you, in place of some of the silicon atoms, you replace them with phosphorus or arsenic, then these impurities do not have 4 electrons, they have 5 electrons. So 4 electrons, they act, since they are taking, it is doping, they are trying to, it is like, what do they say, when people, what is that term called, where people, where the forces, they mask themselves as something else and they take part in movies also they show, I'm unable to get the term, but when you pretend, when you are to be somebody, so they kind of, if you add the arsenic or phosphorus, that atom comes and enters the crystal and starts behaving like silicon or germanium. It also forms the 4 bonds that silicon or germanium would form, but it has that 1 extra electron. So what happens with that 1 extra electron? Arsenic is forming 4 bonds with these 4 neighboring atoms, but that extra electron, which I've shown with the red dot, it occupies an intrinsic interstitial space. Now this extra electron, it becomes delocalized and it starts floating in the crystal because it is not satisfying the valency of any atom. So it starts floating, and what is floating charge? That is what is required to conduct electricity. When electrons can move freely, any charged particle, when it moves freely, it causes conduction of electricity. So these floating electrons improve the conductivity of silicon or germanium, thus making the semiconductor a better conductor of electricity. So when doped with 15 group elements like phosphorus or arsenic, 4 out of the 5 electrons are used in the formation of covalent bonds with 4 neighboring silicon atoms, and the 5th electron becomes delocalized. These delocalized electrons increase the conductivity of doped silicon or germanium. Here, the increase in conductivity is due to the negatively charged electrons. Do you see? Here, what caused the increase in conductivity? The floating electrons. And we know that electrons are negatively charged. So, since they are negatively charged, whenever you dope with an electron-rich impurity, extra negative charge is created, and this negative charge is responsible for negatively charged electrons. So, negative charge is responsible for carrying the electric current. So, such semiconductors which have been doped, such semiconductors are called N-type semiconductors, where N stands for negative. So, because it is electron rich, it is negative charge which is carrying electric current, therefore we call it N-type of semiconductors. So, here the increase in conductivity is due to the electron rich impurity is called N, and is doped with electron rich impurity is called N-type semiconductor. Then comes the second category, that is the second type of semiconductors. They are electron deficient impurities, doping with electron deficient impurities. Now, as I told you that if you have group 14, if I dope it with group 15 elements, they are negatively, they cause negatively charged semiconductors, or they have more electrons. But imagine if instead of doping it with group 15 elements, I doped it with group 13 elements. So all you have to do is choose an element which has one electron higher or one electron lesser. So if I choose an impurity which is from group 13, for example, you have boron, aluminium or gallium. If you take elements from the group 13 and you dope silicon and germanium with any of these group 13 elements, now these elements have 3 electrons in their outermost shell. So when boron or aluminum or gallium, they take the place of silicon, let us say this is silicon being doped, the 3 electrons will form 3 covalent bonds with 3 neighboring atoms. Now this one forms here, this one forms with the lower silicon atom, this one forms, okay, there should be 2 dots here also, this one forms a bond with this neighboring silicon atom too. But what about this one? Boron had only 3 electrons, it forms 3 bonds with 3 neighboring silicon atoms, but this point here, this is silicon, it has 1 electron, but boron does not have an electron. So it creates a hole, a vacancy there. This hole that is created is a deficient electron. There is no electron there. In order to maintain electrical neutrality, there should be 1 more electron here. And in this case, in order to maintain electrical neutrality of this little part of the crystal, there should be 1 less electron. That is why, since this was negatively charged, it is called N-type semiconductor. This has 1 electron less. So when 1 electron is less, number of protons would be more. So it would be, not really, number of protons is also the same because boron has the same number of electrons and protons, but it appears that the positive charge, the electron is deficient, so it appears that positive charge is more. When I explain the movement here, you'll see that actually positive charge is not there. There is only a vacancy. There should be negative charge there, negatively charged electron there, but that electron is missing. So when this hole is created, what happens? Whenever there is a deficiency of electrons, the neighboring electrons, they are, electrons are very good guys. They try to help each other a lot. So anything that is charged actually is really charged and they are good. They try to move wherever the charge is deficient. So they try to cover up for the charge. So what happens? The neighboring electron takes the place of this hole. So when this electron shifts here, what happens? Here there will be 2 electrons, but this part, now this site becomes a hole. When this site becomes a hole, the next electron moves there to occupy that hole. But that creates the hole at the next spot and the process continues. But what is happening here? Electron is moving. When electron is moving, electron is negatively charged, and when a charged particle moves, that is electricity. So, as a result of that generosity of electrons that they try to go and fill up the space wherever there is deficiency, that itself causes an increase in conduction. But what appears to us is, when you pass electric current through such a semiconductor, the electrons will move towards the positive terminal. We understand that. And the flow of electrons to fill up that hole will be in that direction, that if this is, let us say this is the positive terminal of the connected to the silicon sample. So the hole, the electron here will move towards this, and the hole will move here, and the electron will move here, because all electrons will try to move towards the positive charge. but the negatively charged plate, so this is a positive hole, but the negatively charged plate which is here, it appears that the hole is moving towards the negative plate. It only appears. Why does it appear? Because the electron, the hole is only an empty space. It is not a particle that is moving. So the hole is only an empty space, but it is moving towards the negative plate. So we say it is acting positive. It is not positively charged. There is no positively charged particle there, but it is only acting positive. And such type of a semiconductor would be called a p-type or a positive type semiconductor. So let me just read this now. When silicon and germanium are doped with group 13 elements like boron, aluminum or gallium, which contain 3 valence electrons, the place where the 4th electron is missing is called a hole. An electron from the neighboring atom moves to the hole, leaving a hole in its original position, and this hole appears to be moving in the direction opposite to the movement of electrons. It appears that electrons are moving in this direction, but the hole is moving in the opposite direction. So the hole appears to be moving in the opposite direction from the direction of the movement of electrons. So the hole appears to move in the direction opposite to the movement of electrons. Under the influence of an electric current or an electric field, electrons would move towards the positive plate. Through the electronic holes, the electron will keep moving towards the positive plate by moving through the electronic hole. But it will appear that the hole is moving towards the negative plate. So it will appear that the positive electron holes, they will appear to be positive because they are moving towards the negative plate. Actually, they are empty. There is no positive charge there. But since it appears to be moving, the hole appears to be positive, we call it a p-type of semiconductor. So this was conduction of electricity in semiconductors. In the next video, I'll be talking about the applications of these n-type and p-type semiconductors. With this, I'll wind up this video. If you wish to watch other videos of this chapter, please click the link that appears on top of the video. And if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.